All right, we have a lot of exciting things today, so let's get into it. Before we get into the chemistry, there's a couple of meeting announcements. If you're a pre-medical student, AMSA is having a meeting next Tuesday with a guest speaker who's a surgeon. And then something a little bit different is there's an astronomy society at UH. They have a spring social, which I guess is sort of their general meeting type operation. Also, it'll be on Monday of next week. And this is for anybody who's just even interested in astronomy. Don't have to necessarily be a astronomy major or pursuing a career in astronomy. So those are some things coming up. And then today what we'll have are continuation of Chapter 2. So Chapter 2 is, as we said last time, is pretty involved, pretty dense, a lot of things to go over. And we're gonna progress through that today. So we'll get most of the way through Chapter 2 today. There's a couple of remaining topics that we'll have to deal with next time as we finish it up. All right, so what we were ending with last time was a discussion of quantum numbers. These are these three numerical parameters that describe orbitals. We kind of went through in a little bit of abstract detail what they mean. We're going to see it more specifically today, how especially the last two quantum numbers, L and m sub L, that we haven't seen before. But just to wrap up that section, let's do a couple of example problems as we didn't finish up last time. If you have the notes from last time, they're in there. If not, they're short questions. You can jot them down. So the first one that we want to ask is, what is the smallest principal quantum number that has d orbitals? So what we have to remember is that these little letters that we use to describe subshells or individual orbitals, that refers to the second quantum number L. So we have n, and we have L, and we have m sub L. And this letter refers to L. So if L can be 0, 1, 2, 3, and so on. So here we're working a little bit backwards. We gave the hierarchy starting with n going down to L. Here we're kind of going in reverse order. We're giving you a value of L and telling you what's the smallest value of n where that is possible. So if L equals 0, 1, 2, and 3, remember that these correspond to the letters S, P, D, and F. Those are the most common ones. You go on alphabetically after that, although those don't really appear in real atoms. And so what we see is these three numbers. D orbital means that L equals 2. Now what we have to remember about L is that the rules for L is that it starts at 0 and goes up to n minus 1. So depending on what the value of n is, that's going to determine which values of L are allowed. So if we have L equals 2, what's the smallest value of n where we can see that? So n minus 1 is 2, so n is 3. So the algebra is not terribly difficult here. And we get n equals 3 would be the smallest principal quantum number that has d orbitals. So if n equals 1 or 2, you cannot have L equals 2 also, and that would not have then d orbitals in it. But anything that's n equals 3, 4, 5, and so on, this L equals 2 or d orbitals would be an allowed quantum number for that situation, for those situations. All right? So that's one example, just working a little bit backwards. And then the last two are dealing with numbers of orbitals. We talked about some relationships last time. So when you get a problem like this, how many orbitals have the quantum numbers n and L equals, for example, in this case, 6 and 6, the first thing to think about is, are these valid quantum numbers? Because if they're not valid quantum numbers, the answer is 0 and you're done. If the first two quantum numbers don't follow the rules for quantum numbers that we learned, then you can't have any orbitals that would have those. So if n equals 6, what are the possible values of L? So remember, L starts with a 0 and goes up to n minus 1. So L can be 0, 1, 2, 3, 4, 5. Remember, it can be any of these L values. It's not just 1. It's not just the maximum or the minimum. It's any of those numbers in between. But here we have L equals 6. But that's not an allowed value of L when n equals 6, okay? So this is not a valid set of quantum numbers, so there would be 0 orbitals that have 6 and 6 as the n and L quantum numbers. If L is going to be 6, n has to be at least 7. Or if n equals 6, the biggest value of L would be 5. Those two don't match with each other, so you're not going to have any orbitals that have that. And then finally, the last one, similar type of question is, how many orbitals have the quantum numbers n and L equals 7, 5? This time, the pair is okay. So we check that those are a valid set of two quantum numbers, and if n equals 7, L could be as big as 6, so L equals 5 is fine for the n equals 7 shell. So this is an okay set of quantum numbers. Now we have to answer the question, how many orbitals? And so remember that what we're doing here is counting the allowed values of m sub L. Each triple pair of numbers, NL and m sub L, will define an individual orbital. So if we know how many individual values of m sub L are allowed for these two n and L values, then we can count the number of orbitals. So that's one way to go about this. So if L equals 5, remember that m sub L goes from negative L up to positive L, remember all including 0, all values in between. So that means the allowed m sub L values are going to be minus 5, and then we step up by integers. So if we count the number of m sub L values, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to have 11 orbitals that would have the quantum numbers NL 7, 5. Or in other words, this would be the 7H subshell, so not a real subshell, but one that could exist. And if this is the 7H subshell, there'd be 11 orbitals in that subshell. We count those by the number of m sub L values. Now there is the shortcut I introduced last time, which is that if you know the quantum numbers n and L, or even just L by itself is all you really need, we can calculate the number of orbitals with a simple relationship 2L plus 1. So if it's 5 in this case, 2 plus 5 plus 1 also gives us 11, same number. So this relationship comes from the idea that m sub L has these allowed values from minus L to plus L, including 0, which is where you get the plus 1 in this equation. So there's a couple ways to do this one. This relationship 2L plus 1 is going to be sometimes helpful, because especially if we give you a hypothetical subshell with a really high L value, it's not necessarily the best use of your time to write out all the individual m sub L's. So you can remember this relationship. The number of orbitals in a given subshell is given by 2L plus 1. So any subshell with L equals 5, whether it's n equals 6, n equals 7, n equals 8, and so on, any subshell with L equals 5 would have 11 orbitals in it. All right, we're going to come back to these relationships later today, so we'll move on for now, and we'll see them in a different context a little bit later. Now, the first thing we're going to cover today are the shapes of atomic orbitals. As we talked about last time, these atomic orbitals are defined by mathematical functions called wave functions, abbreviated as that pitchfork-looking letter in the Schrodinger equation, psi. And we don't typically think about things mathematically because it's abstract and hard to picture. We actually think about what are the shapes of these orbitals. They tell us probability. The square of the wave function in particular is related to the probability of finding an electron at a certain position relative to the nucleus. And using that probability, then we can define shapes, which are regions in space where the electron is likely to be, let's say, 90% of the time. That's typically how they're drawn. So if we're going to understand the shapes of atomic orbitals, we first need to get some terms out of the way that are going to come in when we describe these. So in a general sense, we have what are called nodes in many atomic orbitals. So a node is a region where the electron has 0 probability. So when we take psi squared, or 4 pi r squared psi squared, which is the radial probability, this would be a region where those functions go to 0. Alright, so like any mathematical function, psi squared or 4 pi r squared psi squared, when you take the radial probability, those can go to 0 in some situations. And again, we're not going to deal with those actual functions to prove that, but that's the situation we have. And then within this, there are two kinds of nodes that we're going to talk about. And as I sort of alluded to, these atomic orbital wave functions, if we were to look at them in their full form, typically they're written in polar coordinates. If you're familiar with that from calculus, that's a coordinate system defined by a radius and an angle relative to the origin. Or you could describe them as x, y, and z coordinates. But in either situation, you have two kinds of nodes, radial nodes and nodal planes, or what are sometimes called angular nodes. So radial nodes would be, as the name implies, a certain radius, a certain value of r from the nucleus. So again, the nucleus is our origin here. That's sort of our reference point. And a radial node is a certain radius relative to the nucleus where the probability of finding an electron is 0. And there's a simple relationship for the number of radial nodes as a function of those quantum numbers. So the number of radial nodes is given by the first quantum number n minus L minus 1. All right, so for a given type of orbital defined by an n and L value, you can determine the number of radial nodes with this simple relationship. Now we're gonna talk a little bit about radial nodes and see how those translate into those radial probability distribution functions we introduced last time, which shows the probability of finding an electron as a function of radius, and those do play into those types of plots. They don't really influence the shape of the orbital. Say the main goal is to understand the shapes of orbitals, and the radial nodes don't really determine that, because essentially it's just some distance from the nucleus where the electron can't be. So in the example we gave last time with spherical orbitals, which many of them will be, as we'll see, if you have a radial node, you're going to just have basically some radius where the probability is 0, and your shape is just going to be two concentric spheres, a sphere inside of a sphere. But the overall basic shape would still be a sphere. The radial nodes don't change the shape of the orbital, they just introduce regions in space where the electron cannot be. But the shape is going to be determined by the number of nodal planes, also called angular nodes. You might see both terminology, so don't be confused by that. And this is basically, as the name implies, a 2D, two-dimensional plane where the electron has no probability of existing. So again, any node tells you that the probability of being there is 0. And in this case, instead of being some distance from the nucleus, it's going to be a plane or a surface where the electron cannot be for that particular wave function. Now, nodal plane is angular nodes is probably a little bit more of a general terminology, because there is one example we'll see today where it's not a nodal plane, it's actually a nodal cone. It's like a cone-shaped surface that exists, but that's a rare example and the only one that we're going to deal with that's a little bit weird in that respect. But nodal planes do dictate the shapes of the orbital, and this is the important one to think about if you're just talking about what shape are they. All right, so let's go through the different types of atomic orbitals that you're going to be responsible for. There's only 3 types that you have to really know the shapes of and be able to recognize. And again, for these types of things on the homework assignments and tests, we might ask you how many radial or angular nodes does this atomic orbital have. We might give you a picture and ask you to identify which atomic orbital it is. So not terribly in depth here, but we do want you to know something about this, because as we'll see later on, the shapes of atomic orbitals influence the types of bonds that atoms can form with each other and some other key properties that we'll see. All right, so let's talk about s orbitals first. Remember that S means L equals 0. We talked last time how the value of L is the primary designator of what the shape of the orbital will be. So every s orbital is going to have the same basic shape. And it's a very simple one for s orbitals. They're going to be spherical. And there's no nodal planes. Remember that the number of nodal planes is given by the value of L itself. Did I put that here, or did I forget? I forgot to do that because I was getting ahead of myself. The number of nodal planes is even easier. It's just equal to L. Okay, so if you know the value of L, you know how many nodal planes there are, and again, that dictates the actual shape of the orbital, which is why it's important. All right, so if L equals 0, we have 0 nodal planes, and that gives us a sphere. There's no surface in three-dimensional space where the electron cannot be. But we can have radial nodes in s orbitals. So if we go to the 1s orbital, and we do, again, n minus L minus 1 is giving us the number of radial nodes. That's going to be 1 for n, minus 0, minus 1 equals 0. So the 1s orbital has 0 radial nodes. And if we look at the radial probability density, remember we talked about these functions last time, which are 4 pi r squared psi squared. It tells you the probability of finding the electron at some distance r from the nucleus. These ones are going to look exactly like we drew last time for hydrogen. So as it turns out, the ground state of hydrogen has its 1 electron in a 1s orbital. So that's exactly the radial probability density we drew last time, is for a 1s orbital. I didn't call it that at that time, but that's what it was. So here's the 1s orbital. It's just a simple sort of parabolic is probably not the right word, but it's a function that has a maximum here, again, some maximum probability at some distance from the nucleus where the electron is most likely to be, but again, there's a lot of different values of the radius where the electron could exist. Now, if we go to the 2s orbital instead, Now n equals 2, L still equals 0 anytime we're talking about s orbitals. But here we have n minus L, sorry, L is 0 still, n minus L minus 1 equals 1. So the 2s orbital is going to have one radial node. And so what does that look like? It's going to be a region where the function goes to 0. So you'll get sort of a double hump. You'll get a little peak there, it goes to 0, and then you have a bigger peak farther away from the nucleus. And again, if we were to project this out into 3 dimensions and draw what this orbital looks like, it's hard to draw in 3 dimensions on a tablet, and especially since I'm a terrible artist, but what you would have is sort of 2 concentric spheres. Where some value of the radius, which I'll highlight in red here, you have the probability is 0, but it's still a spherical shape overall. It's just sort of 2 concentric spheres. A sphere inside of a sphere is the overall shape. And so then this point here is your radial node. That point where the function goes to 0 is your radial node, and there's one of them in this case. Now, one of the great mysteries of life that I struggle with every time I teach this course is, well, okay, so you have a region of non-zero probability over here close to the nucleus. You have another big region of non-zero probability over here farther away. How does it get from here to here if it has to go through a place where the probability is 0? So like, try to wrap your head around that for a second, but not too long, because you'll drive yourself crazy thinking about it. But essentially, it's a process called tunneling. We're not talking about it here, but it's one of those quantum mechanical mysteries of how does that actually happen? How does an electron go from between 2 non-zero regions of probability if it has to cross through a region where the probability is actually 0? And that's just weird to think about. But we don't have to worry about that, but that's one of the things that comes out of this weird quantum mechanical treatment. But this is what you need to know. There's one radial node, and this is kind of then what the probability density looks like. And then the last one we'll do for s orbitals is 3s. So here n equals 3, L still equals 0, n minus L minus 1 equals 2. So we're going to have 2 radial nodes for the 3s orbital. Number of radial nodes, again, is n minus L minus 1. So here we just have 2 peaks and 2 places where it goes to 0. And again, I'm drawing these qualitatively, but the key feature is that you now have 2 radial nodes. Let me draw that again, that's bad. Alright, so we have one there at that radius and one there at that radius. Those are our radial nodes. Okay? So that's the story for s orbitals. They're all spherical in shape, but depending on the value of n, you're going to have different number of radial nodes and then slightly different shapes for the probability density that have that many peaks depending on the value of n. Alright, questions on this one? Alright? Yeah, sorry. I can't see you, but ask, go ahead. Well, that comes out of the mathematical equation that you have. So if you write out the function, again, it's typically in polar coordinates. You have a radial and an angular component. It has a bunch of sines and cosines. And so it works out that way mathematically. The other reason that we'll talk about a little bit later on is that the value of n, as we talked about, is related to the most probable radius. So when you calculate this most probable radius here that's at this peak, and I may not have done it perfectly accurately here, but every time you increase the value of n, your most probable radius gets farther and farther away. So your most probable radius is not going to be really close to the nucleus if n equals 2, 3, 4, and so on. It's going to be something farther away. So they kind of always have that basic progressing shape like that because of, again, the mathematics of the situation and the relationship between the value of n and that most probable, the position of that peak there. All right, that's a good question, probably a little bit deeper than we need to think about things, but again, try to understand these plots and that all else you need to know is that s orbitals are spherical in shape. Now the ones that are slightly more complicated are p orbitals. We're only going to do 2p orbitals because all that's different between 2p, 3p, and 4p and so on is just going to be the number of radial nodes, which, as I said, doesn't really change the basic shape, so we don't have to worry too much about radial nodes in most cases. So for 2p orbitals, here we have n equals 2, L equals 1. And if we want to think about how many individual p orbitals there are, remember we have to think about the possible values of m sub L, or use that 2L plus 1 equation, and we get m sub L is -1, 0, and plus 1. So there's going to be 3 2p orbitals that are all distinct from each other in some way. The radial probability density for these looks very similar. In reality, the radial probability is directional, as we'll see. It's not a sphere anymore, so this radial probability density would be the probability density in some direction going away from the nucleus, not in all directions, because it's not a sphere anymore. But it would still look qualitatively the same. We would have, in this case, 0 radial nodes, because n minus L minus 1 would still be 0. And so for a 2p orbital, it's just going to have that simple appearance there. 3p would have 1 node and so on, but radial nodes we don't think about as much for p orbitals because they're not spherical anymore. That said, the basic shape that we want to be familiar with is we have 3 different 2p orbitals because there are 3 different values of m sub L, and as we covered in general last time, the m sub L values determine different orientations of the orbital in space. So if it's an s orbital, it's a sphere, it can only have 1 orientation, but for anything that's not spherical, it can point in different directions. And so the shape of a p orbital is what I like to call a dumbbell shape, or a figure 8 if you prefer, and they're just oriented differently along the x, y, and z axes. So you have one orbital that's commonly referred to as px, and that's going to be along the x-axis, and it's going to have this sort of figure 8 or dumbbell shape, as it's often called. Now, one thing your book doesn't show, but I think is important to cover now because it will be important in some of the stuff we talked about in chapters 3 and 4, is that the p orbital actually has 2 phases. So even though the probability density is a square of a wave function, is never going to be negative, if you look at the phase of the wave function itself, if you just look at psi itself, the p orbitals have regions that are positive and regions that are negative. And anytime you have a nodal plane, as you cross that nodal plane, you go from a positive to a negative region. And so what the better way to draw these, which is different than what your book does, is to shade one of the lobes to arbitrarily indicate that one of them is positive, one of them is negative. That doesn't matter so much for what we're doing in this chapter, but when we start talking about bonding, it will be important. Okay? So you have 2 different phases, which mean that the sign of the wave function is positive in one x direction, negative in the other, depending on how you write the function. And the nodal plane in this case is just going to be the plane that's perpendicular to that axis. So if it's the x-axis, the yz plane would be perpendicular, if you remember your geometry, and so you're going to have a nodal plane in the y and z direction. All right, and then the other p orbitals are exactly the same shape, just oriented along the different axes. So we have a py that's going to go in this direction as I've drawn the axes. Again, 1 positive, 1 negative lobe. So I shade one of them. And this will have the perpendicular plane, which is all the other coordinates. So if it's in the y direction, the xz plane would be the nodal plane, the one that's perpendicular to that direction. So as you cross the xz plane, you go from positive to negative in the wave function. That's what those colors mean. And then we have pz, which is along the z-axis. And as I've drawn it here, it's arbitrary whether what means positive and negative. I don't specify that. It's not important for us. But it's going to have an xy nodal plane. And again, one region in one direction that's positive and a region in the other direction that's negative. The other thing that I left out a little bit, now I lost my train of thought, but so here's what I want to say. So we have these 3 different m sub L values, and these do not correspond directly to, there's not a 1-to-1 correlation of m sub L with px, py, and pz. So it's not that m sub L equals -1 is px and 0 and so on. It's just that in some sense these are 2 different ways of parameterizing the functions. These m sub L values come from the polar coordinates. These are drawn sort of in a more Cartesian fashion, so there's not really a direct correlation. But the point is we have 3 different m sub L values, which means we have to have 3 different p orbitals that differ with respect to their orientation in space. All right, so those are p orbitals. Those are slightly more complicated. All right, now let's go to the d orbitals. The first shell where we have d orbitals is 3d. And now we get to really test my artistic abilities, which are, as I mentioned, mediocre at best. So for the 3d orbital, we have n equals 3 and L equals 2 now. So d means L equals 2. If we're talking about 3d orbitals, we have 0 radial nodes, because n minus L minus 1 is 0, 3 minus 2 minus 1. But we have two nodal planes, because again, that's given by the value of L. So now we have two planes where the orbital will change phase or has zero probability of existing. The radial probability density, again, is directional, but if we go in one direction, it will look qualitatively similar to the 1s orbital. There's no radial nodes, so you're going to just have a simple function like that. But then the interesting part about d orbitals is their shapes. Now, there are actually two different shapes for d orbitals. This is where they get a little bit more confusing than the p orbitals. There are 5 of them in total, because L equals 2. 2L plus 1 is 5. So there's 5 individual d orbitals, and again, they differ with respect to how they're oriented. But there is one little difference in terms of their shape also that we'll see. So 4 of the d orbitals have 4-leaf clover shapes. The easiest one, I think, to draw and understand is what's called dx squared minus y squared. These do tell you the orientation in some respects. They're not totally illogical. Why is it called x squared minus y squared? I'm not 100% sure why they gave it that name, but it is oriented along the x and y axes, as the name tells us. So now you have a 4-leaf clover shape. In this case, the individual lobes or leaves of the clover are along exactly on the x and y axis. This is a planar orbital in some respect that has some three-dimensional shape above and below the plane. And then if we talk about the phasing on these ones, it's sort of alternating positive and negative as we go around the 4-leaf clover. So this is dx squared minus y squared. And then 3 of the other d orbitals are also 4-leaf clover in shape, but they're just rotated in space relative to this one. So there's the dxy. As the name suggests, it is also in the xy plane, but you take this orbital and you rotate it 45 degrees. So now the individual lobes are in between the x and y axes and not right on the x and y axis. Okay, so we just take that whole thing and rotate it. So what we get, it's a little bit hard to draw in this orientation, but you'll get a lobe that points back, a lobe that points towards you, and then 2 that go in and out in between the x and y axes in that direction, and again, alternating positive and negative. What I'll try to do here to help you is I'll highlight the x and y axes, or the axes that these are oriented along. So that's a little bit big. Can I make this smaller? I don't know. Maybe I can do that. All right, so you have along the x and y axes, a little bit better. That's where that orbital is sort of sitting. Again, it has some density above and below that plane, but the general orientation of it is in the xy plane. Same with this one here, but the only difference is that this one is along the axes, this one is between. So you're just rotating it 45 degrees. All right, 2 other ones that have the same shape are just, again, if you have x, y, you have every other binary combination of Cartesian coordinates also. So you have dxz as well. And again, as the name implies, that's going to be along the x and z axes. And we have, again, a lobe in between x and z in each direction. I don't know if I did a great job with that one, but it's along these axes, same shape, just in a different orientation. And then the last one that has that same shape is the last combination, which is yz. So in that case, we're going to be along the z and y axes. So it's this orbital here rotated 90 degrees to be facing the other direction. And we would have, oops, I'm going to draw that in yellow too. We would have a lobe there, 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 and there. Alright, so again, it's difficult even for a good artist to draw three-dimensional objects, and I don't fall in that category, so I'll give you better pictures in the next slide, but hopefully it helps us to walk through them a little bit. And then the last one, which is the oddball, is dz squared. Alright, so again, the name kind of tells you the orientation. It's along the z-axis. At the onset, this looks like a p orbital, but it doesn't have opposite lobes this time. The 2 lobes are the same phase. And it has what's called a torus, or colloquially a donut, that goes around in the whole thing, like a circular sort of lobe of another phase. So it still has 2 phases. This is the one that I alluded to before that has a nodal cone. It's not a plane that separates the different phases. It's a cone that starts in the origin and goes out kind of like that in all directions. So it's 2 cones that come out from the origin. You don't have to worry about that detail of it. But the dz squared is the one oddball d orbital, which is along the z-axis, and it's the only one that has this ring or torus shape, as we call it. All right, so questions on the shapes. Those are the only ones we have to do. I've covered all of them now, so any thoughts on that or questions before I move on? All right, here is reproduction. I don't know if this is from your, I think this might be from the older version of the book, but these are all the d orbitals in case my pictures were hard to interpret. Again, these ones don't show the phases of the orbital, which right now is not important, but later on will be, not so much for d orbitals, but this shows the basic shapes and how it's basically just, again, this is dyz, dxz, dxy, dx squared minus y squared, and dz squared. Those 5 pictures there kind of show you what those look like, and it's helpful to be able to recognize those for the types of problems we'll do. We're not going to do f orbitals. F orbitals do exist in a lot of elements on the periodic table and have electrons in them, but those are extremely complicated, and I would not be able to draw them, and nor would we expect you to be able to recognize them. All right, so let's just do a couple of sample problems about orbital shapes. Again, this is more of a quantum number question. The first one, which of the following orbital designations is incorrect? So again, we have to work through the quantum number rules, and we have to remember that all of these were given this sort of letter number combination, which means that we have to think about what those letters mean. S, P, D, and F tells us that the value of L would be either 0, 1, 2, or 3. So basically we want to figure out for which one of these combinations are the value of N and L compatible with each other, exactly as we did earlier. So this is kind of a review now. So if this one is N equals 2, the possible values of L are 0 and 1. N equals 2, L equals 0 is a 2s orbital, so that checks out. That one's okay. N equals 3, L equals 1. L can be either 0, 1, or 2. So L equals 1 is allowed. That does indicate a p orbital, so that one's okay too. We have N equals 4, L equals 2. If N equals 4, L can be 0, 1, 2, or 3. So 2 is okay, and if L equals 2, that would be a d orbital, so that works out. And then finally the last one, N equals 3. L can be 0, 1, or 2, as we saw earlier. It cannot be L equals 3, so this one is going to be the correct answer. Okay? So again, that's a disallowed combination of N and L, 3 and 3. It would be called 3F if it existed, but it doesn't exist at all, because in order for you to have an F orbital, or L equals 3, N has to be at least 4. Okay, so again, just rehashing those rules. And then this is another typical type of question we'll give you. We just give you a picture of an orbital and ask you to identify what it is. So the first thing to think about is the basic shape. Is it a sphere, which would be S? Just remember, S orbitals are spheres. P orbitals would be figure 8 or dumbbell shape. And then most of the d orbitals, as we saw, are 4-leaf clovers. So look for those obvious differences, because those are pretty easy to spot. This is clearly one of our d orbitals, the 4-leaf clover, so we can eliminate that choice here. It's not a p orbital at all. But then if we go to which of these d orbitals is it, remember that we have, it's along the x and y axes, as we can hopefully see here. X and y are the two axes that the lobes are oriented along, so that gets rid of dz squared. But then which of these is it? We have to remember that the one that's along the axes is x squared minus y squared. So x squared minus y squared and xy are probably the two toughest to keep straight from each other. But you just have to remember that xy, xz, and yz, the ones that are named as just binary products of coordinates, those fall in between the axes. The one that falls right on the axes would be x squared minus y squared, or z squared if it's along the z-axis. Okay? So that's just a quick example of the type of questions we'll ask you. Anything else before I move on? So we're going to start a slightly different topic now, although it is closely related. Alright, so up until now I've sort of hidden the fact that there is a fourth quantum number. We've talked about the 3, N, L, and M sub L that define orbitals, but there is one more we have to consider when we start putting electrons into orbitals. And so that one is called the spin quantum number. It is abbreviated M sub S. So we have M sub L, now we have M sub S. And it only has two possible values, either plus 1/2, minus 1/2. So plus and minus 1/2 are the only allowed values for M sub S. Can't be anything else. It's the only one that's not an integer, but it only has two possible values. And what we call these is typically spin up or spin down. So that's kind of the language we often use. If m sub s equals plus 1/2, we call it a spin up electron. If m sub s equals minus 1/2, we call it a spin down electron. So that hopefully makes intuitive sense. Now, what does it mean in terms of a physical? We talked about how NL and m sub L all tell us different things about the size, shape, and energy of the orbital. We have a table last time to summarize that. M sub s is actually a property of the electron itself. So this is no longer a property of an orbital. It's a property of an individual electron. And all electrons have this property whether they're in orbitals or not, whether they're bound to an atom or free electrons, as in like the cathode ray experiments. They're always going to have either m sub s plus 1/2 or minus 1/2. That's just the nature of electrons in general. And what it tells us is it's the direction of its magnetic field. So as you probably learned in physics class, if you have charges in motion, you generate magnetic fields. And even though it's a little bit different here because it's we're more quantum mechanical than that, it's sort of the same idea. It has a magnetic field associated with it that either points up or down. And that's what m sub s tells you. All right, so then all four quantum numbers are going to be together, NL, m sub L, and m sub s. These three here designate an individual orbital, and then the last one here is a property of an electron, which could be in that orbital. Okay, so to designate an individual electron and to fully classify that electron, you need all four quantum numbers. NL, m sub L tells you where it is in the atom. M sub s tells you whether it's spin up or spin down. All right, so with those four quantum numbers in mind, m sub s being perhaps the simplest one, the other thing that we notice too is that m sub s doesn't depend on NL or m sub L. It can be plus or minus 1/2 regardless of what the combination of NL and m sub L is. So it has no dependence or no relationship with these first three quantum numbers. It's completely independent. It's just the electron itself, not reflecting the orbital. So that takes us to the Pauli exclusion principle. Again, another very angry early scientist who could cut steel with his glare, I guess. But he came up with the idea, which is that no two electrons, so this is Pauli that's shown here, it's named after him, and no two electrons can have the same, in an atom specifically, so not in all of the universe, but if you have a single atom and you have more than one electron in those atoms, no two electrons can have the same four quantum numbers. So every electron in an atom will have a unique set of those four quantum numbers. You're going to have, as we'll see, some of them, you're going to have duplicates of three of those quantum numbers, but you're not, if all four sort of generate a unique set for each electron. Yeah, you're right. Good. Letting me erase my embarrassing mistake. Wait, no. Sorry. No two can. No double negatives here. All right. This is not English class, but we're not going to put double negatives in the notes. Confuse people. So no two electrons can have the same four quantum numbers. Or another way to think about it is that every electron in an atom has a unique set of quantum numbers. So same means the same thing. Now the implications of this. So remember that m sub s can only have two values, plus and minus 1/2. So that means if we have an orbital which has a specific NL and m sub L value, when the electron goes into that orbital, it can either be plus 1/2 or minus 1/2. Those are the only two possibilities, but you can't duplicate that. So what that means is you have a maximum of 2 electrons per orbital. So if you have an orbital in an atom, you're going to put no more than 2 electrons into that. As we'll see, you don't always put 2 in, but that's the most you can put. Because if you wanted to put more than 2 electrons into an orbital, you'd have to duplicate one of these m sub s values, and then you'd have the same set of NL, m sub L, m sub s repeating themselves, which you can't do. Okay? So Pauli exclusion principle dictates that only 2 electrons at most can go into a single orbital. And then when that situation happens, so when you completely fill an orbital with 2 electrons, which as we'll see is common, it's not like it's a rare thing. But when this situation happens, the spins are what we call paired. So paired just means opposite from each other. One has to be spin up, one has to be spin down. So one of the spins will be plus 1/2 spin up. The other spin for the other electron in that orbital would have to be minus 1/2. And that ensures that those two electrons have a unique set of 4 quantum numbers, the only difference between those two being the last one, m sub s, which is either plus 1/2 or minus 1/2. So that's the situation we have, and Pauli's solution principle tells us that. And what we're really building up towards here, as we'll get to by the end of today, is sort of a description of how do we know which orbitals in an atom have how many electrons in them? So we have to understand that at this point, what we have to understand is that each orbital can have no more than 2 electrons, and the electrons have to be up and down if they're paired in the same orbital. All right, so this gives us now some new relationships that are relevant to the relationships we started with today for a number of orbitals. So if you have a given shell n equals 1, 2, 3, so on, we saw already, or last time, I guess we didn't use this one today, but last time we introduced this relationship, which is that the number of orbitals in a given shell is n squared. So you have 1 orbital for n equals 1, 4 orbitals for n equals 2, 9 orbitals for n equals 3, and so on. And then if you have a maximum of 2 electrons per orbital, that makes it pretty obvious to see then the maximum number of electrons in a shell is going to be 2n squared. So you just double that. Now, that's not to tell you that there will always be that many electrons, but that's the most you can put in there, is 2n squared. All right, so it's, again, depending on only the value of n for a shell. And then if we go to a subshell, which is designated by n and l together, as we saw before, the number of orbitals in a subshell is just given by the value of l itself. The value of n doesn't matter if you're specifying a subshell. It's going to be 2l plus 1. And then again, we saw when we drew the shapes of the orbitals that there were 1 s orbital, 3 p's, and 5 d's, which comes from this relationship. And because we can put no more than 2 electrons in a single orbital, the number of electrons in a subshell is just going to be 2 times 2l plus 1, or if you prefer to simplify, it'd be 4l plus 2. But essentially, again, it's the maximum number of orbitals, and then to find the maximum number of electrons, you just double that because you could put as many as 2 electrons into each orbital. So let's just work through a couple of quick examples that I came up with off the top of my head. So if we're in the third shell, n equals 3, the maximum number of electrons, again, I should probably put max here so you're not confused by that. The maximum number of electrons is going to be 2n squared, or 2 times 3 squared is 18. So in the third shell, you're going to have no more than 18 electrons. And then if we're going to divide those up into different subshells, the n equals 3 shell has 3 subshells. And here the number of electrons is 2 times 2l plus 1. L equals 0 for the 3s. So 2 of those 18 electrons can go into the 3s subshell. For 3p, L equals 1 now, and so the maximum number of electrons that go into 3p is 2 times 2 times 1 plus 1, L equals 1 in this case, and that's going to be 6. So 6 of those 18 electrons can go into the 2p subshell. And then for the 3d, you have 2 times 2 plus 1, L equals 2 for 3d, and that means 10. So of these 18 electrons maximum that you can have in the third shell, you can put up to 2 in the 3s, up to 6 in the 3p, and up to 10 in the 3d. That's how they would divide themselves up if that shell was completely filled. All right, any questions on that? Does that make sense? All right, so what we're getting to now then is how do we know what order to fill the subshells? So we have all these possible subshells in an atom. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, all these different possible subshells. What determines the order that they get filled in? And when an atom wants to do, and this is a pretty common situation in chemistry, an atom wants to achieve the lowest energy possible. Okay, so in some sense you could say atoms are lazy; they don't want to have any more energy than they need. So they're going to try to minimize their energy. Now, how do they do that? There are 2 factors that are kind of competing with each other. So one is you have proton-electron attraction. So the more protons you have in the nucleus, This gives you a stronger attraction to the nucleus, or closer to the nucleus also gives you a stronger attraction to the nucleus. So remember that we didn't see the equations exactly, but if you have two oppositely charged things interacting with each other, the strength of that interaction depends on how many charges there are, so how many protons are attracted to that electron, and also how close to each other are they. And so both of these would lower the energy or make it more negative. So this is in the goal to achieve the lowest energy possible. This is what electrons want to do. They want to get as close to the nucleus as possible. Remember, the number of protons is more or less fixed by what element you're talking about, but the electrons in that atom want to get as close to the nucleus as possible. That would help them lower their energy. But there's a competing problem. There's a competing factor that goes into this, which is electron-electron repulsion. So if you have more than one electron, now before I write this statement out, remember that for the Bohr model, which only works for one electron systems, the ground state is always n equals 1. That's the place where the electron gets closest to the nucleus and maximizes the proton-electron attraction. However, if you have more than one electron, you also have electron-electron repulsions, which raise the energy. So they repel each other, they have repulsive interactions with other electrons that are present in the atom. Alright, so the closer the electrons are to each other, the higher the energy contribution from electron-electron repulsion. Alright, so you kind of have two competing effects. You have proton-electron attraction lowers the energy, electron-electron repulsion raises the energy, and you try to find the balancing point where you get to the absolute minimum of those two terms combined together. So proton-electron attraction says, well, let's put the electrons as close to the nucleus as possible, but if we do that, then they're going to repel each other more strongly because they're going to be too close together in the same region of space, and that would then raise the energy. So it's a matter of finding which arrangement of electrons gives you the best balancing between these two competing interactions. Now, to speak about it more specifically, we have these two terms called shielding and penetration. So if we have a multi-electron atom, remember we can't put them all into the same orbitals because there's only 2 electrons per orbital. So you're going to have some electrons in certain orbitals, other electrons in other orbitals, and the value of n, that first principle quantum number, in some respect is related to how close the electron would be to the nucleus, at least the most probable location for that electron being closest to the nucleus when n equals 1, and then further away and further away as you go to 2, 3, 4, and so on. So if you have a multi-electron atom, you're often going to have some electrons that are closer to the nucleus, and then some outside of that are farther away. Okay? And so what this means is that you have what's called shielding, where those inner electrons partially block the outer electrons from experiencing the full nuclear charge. So shielding is it reduces the nuclear charge experienced by outer electrons. Alright, so if you have inner electrons that are closer to the nucleus than that one, those inner electrons are going to partially block the nucleus from that electron. And they block them from sort of a anthropomorphic way of saying this is they block them from feeling the nuclear charge. All right, they want to experience that attraction to their oppositely charged protons in the nucleus, but there's going to be those electrons that are closer to the nucleus that sort of block them a little bit. All right, and so what this means is that this effective nuclear charge, as we call it, which we abbreviate as ZEFF, Z effective nuclear charge, is always going to be less than the actual nuclear charge for outer electrons. All right, so if you have a large atom that has, let's say, 25 protons in the nucleus, that would be chromium, I think. Anyway, if you have a large atom with I'm probably wrong on that, you guys are going to make fun of me, but anyway, a large atom with 25 protons in the nucleus, the outer electrons are not going to feel like they're attracted to all 25 protons. That plus 25 charge in the nucleus is going to be partially blocked out, and you're going to have an effective nuclear charge for the outer electrons that's going to be smaller than that. And this is the reason then why, if we're talking about energy rankings, the n equals 1 shell is typically lower than 2, 3, and so on. So in general, we'll see that there's exceptions to this, but for a given L value especially, as you go to different values of n, 1, 2, 3, 4, and so on, those values of n get higher and higher energy. As they get further away from the nucleus, they have less attraction to the nucleus, they're partially blocked by the electrons inside of them, so those electrons are going to be in the higher energy positions as the value of n increases. Now if we want to compare two orbitals or two electrons that have the same principal quantum number 2, so now we have the same value of n, which of these is going to be lower or higher in energy? We have to understand this effect called penetration for this. All right, so penetration is the ability of an orbital or an electron in that orbital specifically to get close to the nucleus. And this reduces the effect of shielding, because if that electron has some even small probability of being close to the nucleus, it can sneak inside of those inner electrons for some period of time, and it can get a stronger attraction to the nucleus that way. Again, these probability densities don't tell you what percentage of the time it's here or there, but it tells you the probability of it being there, and for some orbitals you have a small probability of being close to the nucleus, and that then reduces the effect of shielding. And what this comes from then is the radial probability density, 4 pi r squared psi squared. All right, so if we compare that, and this is again r distance from the nucleus, if we have 2s, we saw that 2s is going to be this sort of double peak here. So the blue one is 2s, and it has a node. And then if we do 2p, it turns out that the most probable radius for 2p is actually a little bit closer than 2s. So if I draw this as carefully as I can, the peak for 2p comes a little bit before 2s. So red one's going to be here, 2p. However, the 2s orbital, because of this radial node and because of this little region of probability here, it's able to sneak in and at least at some times get closer to the nucleus. So you would say that 2s orbitals or 2s electrons, there is a better penetrator. It gets closer to the nucleus. And that's the reason then why 2s would be, in terms of energy, less than 2p. So if you have a 2s and a 2p orbital, the 2s orbitals being better penetrators lowers the energy, and so 2s would come before 2p if you're ranking them from lowest to highest energy. All right, so those are the two effects that dictate the order that the different subshells come in. And then the last thing we have to talk about before really getting into how we fill these subshells is what are called degenerate orbitals. All right, now degenerate does not mean law-breaking in this situation. Degenerate orbitals are orbitals that have the same energy. So we saw from the arguments last time that the 2s orbitals are lower in energy than 2p, but then there are some situations where you have orbitals that have the same energy as each other. And when that happens is when you have more than one orbital in the same subshell. So orbitals in a given subshell, orbitals with the same n and L value, are all going to be degenerate with each other. So, for example, we just talked about the 2p orbital. The 2p subshell has 2 times 1 plus 1, which is 3 orbitals. Remember, we drew those earlier today, so those are the 3 different p orbitals that change their direction from x, y to z. All 3 of those orbitals have exactly the same energy. So those 3 orbitals have these sets of quantum numbers but all 3 of these would have exactly the same energy as each other. So the orbitals in a subshell, if there's more than one of them, will all be at exactly the same energy. So that's the situation for 2p. That would be the situation for all 5 3d orbitals. They'd be at the same energy. If you have 4f, there's 7 of them, all at the same energy as each other. So the energy levels, which we kind of already introduced at the very beginning of this section, are only determined by n and l. So if an orbital has the same n and l values, it will have the same energy. That's the only thing that determines the energy of that orbital. All right, and then what we have to talk about last before we start talking about how to apportion electrons into orbitals is what's called the Aufbau principle. So we've talked in some level of detail, not terribly detailed, what are the factors that determine the relative energies of orbitals and which ones are the same energy as each other. We can sort of rank them now, but as we'll see, we don't have to memorize the order. And the Aufbau principle, which is German for building up, Aufbau means building up in German, is the principle that when we add electrons to the subshells, we have a multi-electron atom, especially where this is important, the electrons are added one at a time, and you always put the next electron into the lowest energy orbital that's available. Into the lowest energy orbital or sublevel, more generally available. All right, so when you're adding electrons to atoms, you're going to add the first electron is going to go into the lowest energy subshell, and then once you fill that subshell, you're going to start adding electrons to the next one, and the next one, and the next one, until you run out, until you've added all the electrons that that atom or ion has. And then the ground state configuration would be whatever that arrangement is, the arrangement of electrons into those subshells. And it's the arrangement that has the lowest possible energy. So we're going to figure out how many electrons each subshell has, and then we're going to write that out in the notation I'll give you here in a second, and that dictates then the ground state of that element. So the arrangement of electrons that gives you the lowest possible energy. And we do that again by following the Aufbau principle. We add the electrons into the lowest available subshell, and then we keep adding them and adding them and adding them until we run out of electrons and we've filled all the available subshells with that number of electrons. All right, so for each sublevel then, we're going to write this sort of notation, NL with a superscript, where X tells us the number of electrons in that subshell. N is the first quantum number, or N, that defines that subshell. So N and L mean the same thing. So N has the same definition. L, we use the letter designation, S, P, D, and F for atoms on the periodic table. So we don't write the numerical value of L when we do configurations, we write S, P, D, or F. So you may have seen these before if you took high school chemistry or Chem 1301, and what we're going to do is we're going to write out each subshell and indicate with a numerical superscript how many electrons each of those subshells has until we have all the total electrons that are in that multi-electron atom. Now you might be wondering at this point, well, how do I know what order the subshells come in? And some of you may have seen, I think your book probably has it, these little like diagonal charts that list all the subshells, and you draw diagonal lines through them, and that gives you 1s, 2s, 2p, 3s, 3p, so on. The way that I like to do it, which I think you should all get in the habit of doing because you're going to have this information on all of your tests, is to use the periodic table to tell us what order we fill all the subshells in. Okay? So the periodic table is not just randomly organized, it actually has meaning to it, and the real meaning of how this table is organized is based on the subshells that get filled and what order they get filled in. And so what we do then is, as we're adding electrons into multi-electron atoms, we step through the periodic table in numerical order, and each time we go through, we fill that subshell that we get to that's represented by that position on the periodic table until we get to the element we're interested in and we stop. Okay? So we'll see how that works with a bunch of examples, but essentially this periodic table is organized into subshells. All right? So the rows of the periodic table are related to the first principal quantum number n. These are called the periods of the periodic table. So that's what period means, is each numerical row going down from 1 to 7. I think they've completely filled in row 7 by now with a bunch of artificial elements, but our periodic table is a little bit outdated, but those we don't need anyway. All right, and then what you have then is each of these sort of sections of the periodic table represents a subshell. All right, so I'm going to have to get different colored highlighters here. Let's do a light blue. And so these two columns here, I'll get a bigger highlighter. All right, so these two columns here, which I'll put in blue, so you guys get to watch me color today. Aren't you jealous? You can do it yourself if you have. All right, so those two columns that I've labeled in blue, I'm bad at drawing brackets. Let me just draw a square bracket. That is the NS subshell. So as we travel through these parts of the periodic table, we're adding electrons. The next electron will go into the 1s. This one over here, I should point out, is also the 1s. It's out of place on the periodic table for reasons we'll understand next time. But these two columns are primarily the NS block. So as you go to the different rows, this is 1s, 2s, 3s, 4s, 5s, and so on. And now I have all these little rectangles I want to get rid of, because I accidentally touched the screen. All right, so that's the S. Now if we go to a different color for P. So the P orbitals, now, and the numbers of the column should make sense. So remember that we have 3 P orbitals for every P subshell. 2 times 3 is 6, a maximum of 6 electrons that can go in there. So these 6 columns are all of our 2p columns, excepting helium, which doesn't have any p orbitals filled in its ground state. But those 6 are the NP. You'll notice that the first p block does not appear until the second row of the periodic table, which is 2p. We talked about 2p being the first p subshell. So that's the p block. And then we also have 10 columns that are the D, what are called the D block. I think that has some sort of prison connotation, but not in this sense. So these 10 columns here, remember there's 5 d orbitals, so a maximum of 10 d electrons that can go into them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those 10 columns, I need to get a different color for that. These 10 columns they're not the ND, they're N minus 1D. All right? So what that means is that if we're in the 4th row of the periodic table where N equals 4, this is actually the start of the 3D block. It's not the start of the 4D block. So these are offset a little bit. In other words, the 4S comes before the 3D. That's where those sort of orders kind of get out of line a little bit, but you don't have to memorize that, because if you go through the periodic table in order, you see that we have 4S is here, and then we go to the 3D. This row is 4D. This row is 5D. All right, and then the last one, which we won't deal with a whole lot, but is still sort of important, come on, are these guys down here. These are displaced, not for any particular reason, but just to make the periodic table more readable. These 2 columns come out of here. You see there's a discontinuity where we go from number 57 to number 72. So these 14 columns, which are the F block, they come out of that. So if we wrote the periodic table in the normal order, it would just be extremely long and unwieldy. So we just take these out and put them at the bottom. So this is going to be 4F and 5F. So these 2 columns here, I'll label at the bottom, are the N minus 2F. All right, so this first row comes out of the 6th row of the periodic table, so it's the 4F. The second row comes out of the 7th row, so it's 5F. Now this might not make a lot of sense right now, but when we start using it, I hope you'll see that it's a really powerful way of being able to predict any electron configuration for any element on the periodic table. Now there are some predictions that will be wrong, but we can get the vast majority of electron configurations very accurately by using the periodic table. So let's start to do that, but we have one more thing to define before we talk about this. So the electron configurations typically don't indicate the spin. They're going to tell you, again, 1s, 2s, 2p, and how many electrons are in each of those. They don't indicate whether those electrons are spin up or spin down. But if we cared about that, if we wanted to also define the m sub s values, the plus 1/2 or minus 1/2, if we want to do that, we have to consider what's called Hund's rule. So when you have degenerate orbitals being filled, Hund's rule only applies to degenerate orbitals. If you're putting two electrons into the same orbital, remember that one has to go up and one has to go down. There's no exception to that. But if you're filling degenerate orbitals, you have a choice for how you arrange the electrons. And the way that works, that gives you the lowest energy, is you're going to first put one electron into each orbital. So before double filling any degenerate orbital, you put one electron into each one. And all of those in that same subshell would have the same spin. So you singly fill each degenerate orbital before you go back and start pairing electrons into the same orbital. And so another way of stating this long rule is you just want to maximize the number of unpaired electrons. Alright, so we want to make sure that you have the most possible number of unpaired electrons, not violating the Aufbau principle. You still always fill lowest energy to highest energy, but in a situation where you have a set of degenerate orbitals, you start filling each one singly with the same spin before you go back and pairing them up with the opposite spin. So when does it matter? Again, it only matters for degenerate subshells, or specifically partially filled degenerate subshells. If you completely fill a subshell, all the electrons will end up paired anyway, so it doesn't matter in that sense. But if they're partially filled subshells and you have a choice for the arrangement of spins, then you want to maximize that unpaired spin. Now, without getting into detail about the quantum mechanics behind this, why is this true? By doing this, you minimize electron-electron repulsion. There's also a quantum mechanical term called exchange energy that we don't have to worry about, but the simple way to think about it is that by putting two electrons into two different orbitals before pairing them up, you're minimizing electron-electron repulsion. So if we have a set of p orbitals, px, py, and pz, if you put if you have two electrons in there, let's say, if you put both electrons into px, they're going to be in the same region of space in the x direction, and they're going to interact with each other more and have greater repulsion. But if you put one electron in px and one electron in py, they're spatially separated, one in the x direction, one in the y, and that gets them farther away from each other and minimizes repulsion. So that's kind of the reason why. And then there's also this quantum mechanical thing called exchange, which is why they should have the same spin, both either up or down. Now this doesn't matter for most electron configurations, but if we start asking you about spin, or we start showing you diagrams, as we'll see here in a minute, that show the electrons as being either spin up or spin down, you need to keep Hund's rule in mind when identifying which of those represents the proper ground state for that atom. Okay? So let's do a few examples. We'll not start at the very beginning of the periodic table, but let's start with one that's a little bit interesting, number 5, boron. And let's figure out what the electron configuration of this is. Okay? So to do this, we go back to the periodic table, and I'll go to the labeled one so that we can see it clearly, and we're going to just go in order all the way up to atomic number 5 until we add that many electrons. So we start at number 1, that's 1s, and that's 1s. We have 2 electrons that go into 1s. After 1s comes 2p, so we have 2p1, 2p2, and then to get to number 5, we go over to this section. This is the 2p block. So that 5th electron goes into the 2p subshell. So again, it's 1s1, 1s2, 2s1, 2s2, 2p1. We stop because that's the element we're interested in. All right, so when we write that out, we get, this is how we would write it, 1s2, 2s2, 2p1. And if we want to write then the population or the spins of those electrons, we use up arrows to indicate plus 1/2, down arrows to indicate minus 1/2. So our 1s orbital has 2 electrons in it, so one of them has to be up, one of them has to be down. 2s also has 2 electrons in it, so one up, one down. And then when we get to the 2p, we only have 1 electron left. Now, in reality, you could put this one electron in any of these three orbitals with any spin up or down, and that would give you the same energy. There's no distinction. Remember, all three of these orbitals are the same energy. All the spins up and down are the same energy, so it doesn't really matter. Conventionally, we usually fill left to right, and we go spin up first. We don't have to do it this way. So that's one way to do it. We put the one last electron in a 2p that way, but I could have done any of these combinations. I could have done that. I could have done that. Could have done that, and so on. You don't put more than one electron because there's only one electron in the 2p, but it can go in any of these three orbitals up or down. Like I said, the convention is to fill them left to right and start with spin up, but you might see problems in the homework where that's not necessarily the case, and you have to recognize that all of those possibilities would be the same energy for that 2p orbitals. You have to fill 1s and 2s completely. There's no exceptions to that because that's the Aufbau principle. These come in order of energy, but once you get to this last one, you only have one electron left. Again, there's a few choices for how you do that. If we go one over to carbon, which is atomic number 6, so let's go back to the periodic table. So we're going to go to atomic number 6 now, and again we go numerical order. 1s1, 1s2, 2s1, 2s2, 2p1, 2p2. So that 6th electron will also go into the 2p subshell because we're still in the 2p block of the periodic table when we get to carbon. All right? Hope you guys, yeah, I think you can see the yellow thing. Okay, I can see it, but it matters more if you can see it. All right, so for carbon, we just add the one last electron, and it still goes into the 2s because the 2p, because the 2p is not completely filled yet. So if we just write the configuration, it would look like this. But then again, for the spins, this is the first time where we'll see Hund's rule come into play. So we still pair the electrons in 1s and 2s, but then for 2p, we have 2 electrons and 3 orbitals to put them in that are all degenerate. And so there's a lot of possible combinations, but the key point here is you have to put them in 2 different orbitals and they have to have the same spin. So again, the conventional way to do that would be like this. First 2 orbitals filled, both with the same spin. And so this illustrates Hund's rule. Now I want to be clear that this is not the only way to do it. We could have done that. 2 different orbitals, still the same spin. We could have done that. 2 different orbitals, still the same spin, or we could have done them in down combinations across, so there's going to be, in this case, I think like at least 6 different combinations that would all work for a P2 configuration. Conventionally, we would draw it like this, but it doesn't have to be like that as long as it's 2 separate orbitals, both electrons, same spin, both up or both down. All right, so that's an example of some other ones. Let's go a little bit deeper into the periodic table and talk about sodium, Na, and magnesium, Mg. And so in this situation, what we're going to do is again go back to the periodic table. Now we have 11 electrons to put in there, so that's a bit more. But we still follow the same approach where we just go in numerical order. So we have 1s1, 1s2, 2s1, 2s2, 2p, 1, 2, 3, 4, 5, 6. And then when we want to go to Na, which is the next one, we have to drop down to the 3s block. So that last electron goes into 3s, so we have 3s1 would be the last one filled. All right, so again, we fill the 1s and 2s and 2p's. We go, as we saw, 1s2, 2s2, 2p6. The very last electron goes into 3s1. Now, there is a shorthand way that we often write heavier elements. And so this core here, which is 1s2, 2s2, 2p6, that's 3 completely filled subshells. And it corresponds to the atomic configuration of this element here, Ne, which is neon. Now, as we'll talk about in more detail last time, this last column of the periodic table is called the noble gases. And so very often what we do for electron configurations is we just abbreviate all of those inner electrons, all of those completely filled subshells, we just abbreviate them with the nearest noble gas. So sodium is here, number 11. The noble gas that comes before that is neon. And so these first 10 electrons that we put in correspond to the neon configuration, Z equals 10. And so instead of writing out this whole thing, which especially for heavier elements gets really, really long, we often just write it as this. We put these in brackets as just Ne, and then we only indicate the partially filled subshells that come after that, in this case 3s1. All right, so we use the nearest noble gas to abbreviate the core electrons, what we call it, or the inner electrons. So those are going to be indicated with brackets. Now you'll have to be familiar with both notations, especially for most of the questions on this topic are going to be multiple choice. We're not going to have you type out very long configurations, but if we give you multiple choice questions, we might have the long form, we might have the short form. You need to be familiar with both, but this is commonly how it's done for heavier elements. If we go to magnesium, which is just one more to the right of sodium, again we can find magnesium on the periodic table, which is number 12, Mg here. And we go to the noble gas that comes before that, which is still neon. So instead of writing out all of those subshells individually, we could just write neon in brackets, and then we go down here to magnesium, which is going to be 3s1, 3s2. So we only have to write again those subshells that come after the nearest noble gas. So the shorter way and the fast way to write this one would be just neon 3s2. Has one more electron than sodium. That last electron still goes into 3s because it's not completely filled yet. Now the last thing I'll define today, and I think I'm going to punt the rest of this till next time, is what are valence orbitals or valence electrons. These are what we refer to as the outer electrons. And in the situation of what we call main group elements, again there's some definitions we're going to pick up in more detail next time, but main group elements are those that occur in the S and P blocks. So they either are in the first two columns of the periodic table or the last six. They're in those parts of the periodic table. The definition for valence electrons are the electrons with the highest principal quantum number. All right, so all of the valence electrons would come after the noble gas that's in the in the brackets, but it would be any of those that have the highest principal quantum number n. So sodium would have one valence electron, which is this 3s electron here. Magnesium has two valence electrons, which is these two 3s orbitals, 3 less electrons here. They both have the highest principal quantum number n. So the importance of valence electrons will become more obvious in chapter 3, but we do want to define it now. So we will punt these last couple examples until next time and pick up with the rest of chapter 2 next week.